Welcome to tutorial 27, where we're going to be looking at transistors. Now, transistors are one of the earliest electronic devices and the building block of the whole development of computers. Let's look very quickly at a couple of transistors, what they look like and how to identify them. So here we go. Transistors come in many different packages, from the small to the much larger, with big heat sinks because they dissipate a lot of heat. And they come in many different pin configurations. They have three legs. We have an emitter, a base and a collector. This is for an NPN transistor here. This is our symbol. This is for a PNP transistor that we don't really need to know for GCSE. In most of our experiments and activities, we're going to be using the BC109. As such, I've shown you how the legs can be identified. The best way is to turn the transistor upside down so the legs are pointing at your eyes. You will see a little tab. The leg next to the tab is the emitter tab, E. The emitter leg. Then next to that is the base, and then away from that is the collector. The best thing to do is when you put them in the circuit, just put them in line. Here we go, as I've done here. Put them in line, just 1, 2, 3, and then label them so that you know which is which. In my case, I've got collector, base, emitter. So let's look at our activity that we're going to do, first of all. And we're going to look at how the transistor turns on and off. So this is my circuit diagram. I have my transistor, the BC109, with the emitter leg going down to ground. The collector leg is going to be connected to positive via a 1K resistor, and the base is going to be connected to a 22K ohm resistor. And it always needs, the base always needs a resistor in series with it here, and that is to limit the amount of current flowing into it to protect it, because otherwise it will get extremely hot. And then we've got a potentiometer, potential divider here, varying the voltage between 0 and 5. And what we're going to do, we're going to look at the relationship between V in and V out. So as we increase V in from 0 to 5, what happens to V out? Now I should point out that V out here is across the collector. You will see in the future possibly where the output voltage is across the emitter, and we'll come to that in a while. So let's do the experiment. So I've got 2 voltmeters, one connected to V in and one connected to V out. And at the moment V in is 0 and V out is 5. So I'll write that down straight away. So V out is 5 volts. So I'm going to increase V in, but first of all I'm going to go all the way on V in, all the way up to 5 volts, and you should see V out change. So V in is now 5 and V out is 0. So I'm going to enter that onto my sheet. So at some point there is a crossover, and that's the relationship that we're going to look at. So let me go back to V in as 0, and I'm going to start increasing V in, and let's watch V out. What happens to V out? So V out is now just starting to change, or it was, there we go. V out is now about 4.6, when V in is 0.68 of a volt. So for ease sake, I'm going to write in 0.68, and V out is 4.5. So let's increase V in a little bit more. So I'm going to go up to 0.75, or as close as I can. So 0.76 is V in, and V out is 3.9. So at 0.76, V out is 3.9 volts. Keep increasing. I'm going to try and go up to 0.8 of a volt. I know that these little steps are quite critical here. So now V in is 0.8, 3.5. I'm going to go up to 0.85 of a volt if I can. And V out is 3. 0.92 and V out is 2.3, so 0.92, 2.3. Let's go up to 1 volt. Our meter is turned off. So at 1 volt, 1.5. And 1.25. And V out is pretty much 0. So we've now gone down to 0. So that means now that V out will remain at 0 all the way through the remainder of our values of V in. So let's plot our graph and look at the results. So let's have a little look at our graph. Hopefully your graph turned out very much the same as mine once you'd plotted all of your values of V in and V out. So as we can see, we have a graph that starts out with V in as 0 and V out as 5, and then at some point very quickly, somewhere around the region of V in being about maximum of about 1.1 volts, but starting at about 0.7 of a volt, we can see that V out becomes 0. So you're asked to plot the 3 regions on the graph, and the 3 regions are firstly where V out is off because the transistor is off. This portion here is known as the linear region, and then finally where V out was 0. In other words, the transistor is said to be saturated, i.e. it is on. Now that might seem slightly unusual in that V out is 0 but the transistor is on. So let's have a quick look at that and see if we can explain it. So V in is changing from 0 to 5, which means the voltage at the base of the transistor here is increasing, and at some point where V out has started at 5 volts, it eventually goes down to 0. Now, this transistor, when the base voltage reaches 0.7 of a volt, starts to turn on. At the moment, this is like a really large resistance. Therefore, V out is currently 5 volts, because this is a very small resistance. It's like a potential divider. But when the transistor starts to turn on, this resistance starts to get smaller, and eventually it becomes like a short circuit. So it's like a wire going from there down to there, and therefore V out goes from 5 volts down to 0, because if there's a wire across here, it's connected directly down to ground. So V out goes to 0, but the transistor is on, which is why we say when the transistor is on, it is saturated, i.e. current is able to fully flow. Now where does current flow? Current is flowing from 5 volts through the collector, IC, through this little junction here, through IE, down to ground. And then any current flowing through here also flows down through here, and we'll look at that in the next example. So when the transistor is on, V out is 0. When the transistor is off, because of this huge resistance, V out is 5. And it starts to turn on at about 0.7 volts. This is the end of this activity. So in activity 2, we're going to be looking at the switching action of a transistor. We're going to be looking at how it can turn on a bulb, and the bulb is in its collector part of the circuit. And if we remember from activity 1, we know that when the transistor is off, V out is 5 volts. And if that is 5 volts, the bulb will be off. So when the transistor is on and Vout drops to 0 through the collector emitter junction, therefore this bulb will be on. So when it's off the transistor, the bulb is off, and when the transistor is on, the bulb is on. Now, we've got this little arrangement here that's going to alter V in, and we're going to also be looking at VB here as opposed to the voltage V out, because we know what happens to V out when we turn the transistor on. So, the first question that we're asked is, what is the voltage V in at which the bulb turns on? So let's have a look. At the moment, V in is 0.83 of a volt, and VB is 0.68 of a volt. So I'm going to increase my voltage, and the bulb comes on fairly sharply. So I'm going to turn the bulb off, and now I'm going to turn it on. There we go. So that's quite bright. It's not fully bright, but that's good enough for our readings, and we can see that V in is 1.24 volts and VB is 0.73 volts. So 1.23 volts, 0.73 volts. And that stands up with what we looked at before with our graph, that the voltage at the base turns on at about 0.73. That was where it started to turn on last time. When we looked at V in last time, it was actually fully on at 1.1, but that's because we have a voltage drop across this resistor, which is what we're going to look at. So, what is the voltage drop across the 2.2 k ohm resistor? Well, if we have 1.23 volts here and 0.73 volts there, we must have 1.23 minus 0.73, and that's easy maths, 0.5 of a volt across that resistor. So, calculate the current flowing through the resistor. Well, we know that we've got 0.5 volts across that resistor, and we know the value of the resistance. So therefore we can calculate the current flowing through it, because voltage divided by resistance gives us current. So 0.5 of a volt divided by 2,200 ohms, 2.2 exponent 3, equals, engineering button, shift engineering button to put it into milli, 0.22 milliamps. So what we're saying here is that we have 0.22 milliamps flowing through that resistor. And therefore, if it's flowing through that resistor, it is flowing into the base of that transistor. What is the current? Look at what is written on the bulb, needed by the bulb to turn on. Well, I know that this bulb is a 6 volt, 0.06 of an amp bulb. Therefore, it is 60 milliamps, 60 milliamp bulb. In other words, it's saying that it requires 60 milliamps for it to be fully on. Anything less than that and it won't be bright enough. So our bulb is on and we have a very small current flowing into the base. Therefore, this transistor must be doing some form of amplification. If we look here, we've got 0.22 of a milliamp flowing into the base, and we want 60 milliamps flowing through there, and we know we must have about that because that bulb was nicely on. So this small current is turning on a big current. And calculate the current gain. The current gain is known by these little initials here, HFE, and that is worked out by the current in the collector divided by the current in the base. So we know that the current in the collector is 60 milliamps because that's the current flowing through the bulb, divided by the current through the base, which is 0.22 milliamps. So by how much is that current being increased? So 60 exponent minus 3, current in the collector, divided by 0.22 exponent minus 3, the current flowing in the base, equals 272. So what we're saying here is this has a large current gain. The transistor has a gain which allows this small current in the base to turn on a current 272 times bigger than that in the collector. So it's acting, if you like, as an amplifier. It's an amplifying switch. Finally, calculate the current flowing in the emitter. Well, it tells us that the current flowing through the emitter is equal to the current flowing in the collector plus that current flowing in the base. So if we look at here, the current flowing through the emitter is equal to the current flowing through the collector plus the current flowing through the base. So those two added together come down through here, down to ground. So let's add those up. So we know that we have 60 milliamps plus 0.22 milliamps equals 0.06022. In other words, 60.22 milliamps. And the important thing to note here is because that was such a high gain, actually the base current doesn't really contribute to that whole current calculation to do with the emitter. In other words, we can almost ignore that base current. So hopefully this has explained a little bit better the processes involved in a transistor switching. In activity 3, we're going to look at how the transistor can be used as a light sensitive switch. So in this circuit we've got our bulb again. It is quite important once again that we use the 6-volt bulb here. We've got a LDR now in our circuit replacing a variable, and I do have a variable at the top of the circuit here, and this is being used for sensitivity purposes because of course the voltage at this point will vary dependent upon light, and the amount of voltage is critical to turn on the transistor, and we may have a room that is slightly darker or lighter than other rooms, and therefore we need to be able to vary this to give us some accurate readings. So let's look at the circuit. So here is my circuit, and at the moment the bulb is off. And what I'm going to do, I'm going to turn it on so we can all see what's happening. And then I'm going to turn the variable resistor, which is the potential divided with the LDR, and I'm going to turn it so the bulb just goes off. There we go. So the bulb is now off, and our voltages, at Vin we have 0.828 of a volt. I'm just going to put that to 2 decimal places. I'm going to put this one to 2 decimal places. You can see that the bulb has come on as I pass over the LDR. So Vin is 0.84 of a volt, and VB, the voltage at the base, is 0.68 of a volt. And by now we know what voltage we need to turn on that LDR. So now I'm going to cover up the LDR, and you will see the voltage at Vin start to rise. And the bulb has just started to come on now, and it's coming on a bit brighter. Vin is now at 0.96, VB is at 0.7. I'm going to cover up the LDR completely. You should see the bulb come on quite brightly, and now the bulb can be considered to be fully on. And the voltage at which it is on is when Vin is 1.63, but once again, more critically, it's when VB is 0.76 of a volt. Let's move on to activity 4. In activity 4, we're going to look at how we can latch on the light sensitive switch that we previously built. And the component we're going to use for this is called a thyristor. Its code that I'm going to be using, this is my selection, is the TIC106D. It also goes by the name of SCR, which stands for Silicon Controlled Rectifier. It works a little bit like a transistor, but because of the term rectifier, it actually has a symbol very much like a diode, which is also a rectifier. So it has three legs: the anode, the cathode and the gate. Sometimes the cathode has the letter K indicating it. So let's look a little bit at the circuit. Now we've changed the circuit a little bit. We still have the same input where we have the LDR and the 22K variable to alter the sensitivity, which goes to the base of the transistor. But instead of the output being across the collector as we've used previously, now the output, i.e. going to the gate, is going to be across the emitter. Sometimes this circuit is called an emitter follower. What I'm going to do first of all is just show what happens as that base voltage rises and what happens to the voltage here. So at the base I currently have 0.9 of a volt, and as I increase the base you can see that the voltage increases from the LDR circuit. But what's happening here at the gate of the thyristor, which I haven't got connected at the moment, so as I increase that base voltage, that gate voltage also increases. So previously the collector voltage was high and then went low when we increased that base voltage. Now we can see that this emitter voltage increases as we increase the base voltage. Right, let's connect in the thyristor. Okay, now the bulb has come on, so I'm just going to turn this circuit off and turn it back on. Alright, I'm just going to adjust it slightly. I'm going to turn it off. There we go, that's better. So the bulb is now off. So I've adjusted the sensitivity so that the bulb is off in the light. So in the dark, let's just change the range on our voltmeters and turn it off again. They take some setting up, these circuits, sometimes. There we go. So at the moment, what happens? The bulb is off. Now I'm making it darker, and at some point the bulb comes on. So I'm now going to remove my hand. What happens to the bulb? The bulb stays on. In other words, it is latched on. It doesn't matter what I now do to the LDR, that bulb stays on, which of course causes us a bit of a problem because we want to turn the circuit off. So I'm going to turn the circuit off by powering it off and then turn it back on again. So first of all, at what voltage of the base is the bulb coming on, and what is the voltage at the gate? So here we go. I'm going to increase the voltage at the base. We're up to about 0.991 volt. The gate is at 0.4, and there we go. That was about 1.17 at the base. And now the gate pulse is pretty much held at 0.78. So let's write that down. What is the voltage, VB, at which the bulb turned on? Well, it was about 1.17 volts. What is the voltage, VG, the gate voltage at which the bulb turns on? Well, it's about 0.78 volts. If you increase the light once the bulb has come on, therefore removing the gate pulse, does the bulb go off again? No, it does not, because it is said to be latched. How can the bulb be turned off? So let's have a little look at what we can do to turn this bulb off. At the moment, this bulb is connected to the anode of the thyristor going down to ground. So once this gate pulse comes high, above 0.78 of a volt, let's just call it 1 volt at the moment because that's the general value given. Current is flowing from 5 volts through the bulb, through the anode cathode down to ground. So if we remove the current flowing through the anode-cathode junction of this thyristor, i.e. from positive to negative, we stop the current flowing through this thyristor and therefore we turn it off. So I'm going to remove the bulb and the bulb turns off, and now I'm going to plug the bulb back in again so you can see it, and the bulb doesn't come on. So the thyristor turned off. I turn it on, the bulb comes on. I remove the current flowing through the thyristor, plug the bulb back in. It doesn't matter how I remove that current. If I were to remove the current flowing through that wire, the same thing would happen. That is that wire, I pull it out. The bulb goes off, I plug it back in, the bulb remains off. I latch it on again. So in essence what I have to do, I have to put a method of breaking the circuit. And the best way of doing that is to actually put a push to break bulb in the circuit with the bulb, sorry, a push to break switch in the circuit with the bulb and the thyristor. So there is my gate pulse. So I've got this push to break bulb, and when I push the switch, it breaks the circuit, current can't flow through it, as opposed to our push to make switch, and we have stopped the current flowing through the thyristor. Of course, the problem is, if I break the circuit and my circuit is made, as soon as I reconnect it again, the bulb will of course come on, because the thyristor is being continuously triggered by my hand being over the bulb. So I'll remove it, put it back in, trigger it again. This is how a thyristor works. In activity 5, we're going to look at how we can create a time delay to our previously built circuit. In other words, when we cover up the LDR, instead of the bulb coming straight on and latching on and remaining on until we remove the current flowing through the thyristor, we are now going to have a little delay. In other words, it's going to wait for a while until we reach a certain voltage at the base before that bulb comes on. Now we do this by using a resistor capacitor network, so in other words a charging capacitor network, so that the voltage at the base won't reach its turn-on voltage until after a certain amount of time. I'm not going to do the calculation on that right now. So let's look at that circuit. So here we go. At the moment we have pretty much 0 volts across the base. It's actually 5.5 millivolts, so in essence 0. But as soon as I turn on my power supply, you will see that voltage start to climb, because it's quite dark in here anyway, and therefore that capacitor is charging because there is a voltage across that resistor. Now we're up to 0.2 of a volt. So I'm going to now cover up the LDR, and you will see that voltage climb a little bit quicker. And we're up to 0.6 of a volt. Now we know that the base turned on at about 1.2 of a volt. So any second, there we go, and our bulb comes on. I remove my hand, the bulb is latched on. I remove the bulb, which turns off the thyristor, but I now put the bulb back in and it comes straight back on, because the voltage at the base hadn't dropped below its threshold value. But now it is quite close to that threshold value, so I might try removing the bulb now, which should turn off the thyristor, plug the bulb back in, and it doesn't come back on now because that voltage is lower. I cover up the bulb, the LDR, and the bulb comes back on. Now actually, it's slightly more fun watching this on an oscilloscope. So what I'm going to do, I'm going to turn this off, I'm going to turn this on, I'll plug my voltage, so the voltage across the base is now going to go into the oscilloscope, and I'm going to discharge the capacitor by connecting the positive leg down to ground. So you'll see that line drop, there we go. So now I'm taking that wire out and I'm going to turn my circuit on, and you will see that line start to climb. That is the capacitor charging. I'm now going to cover up the LDR, and that line will go quicker. So we're up to 0.6 of a volt, as it's 0.2 per division, 0.8 of a volt, 1 volt, and there we go, and our bulb comes on. And when I remove my hand, you'll see that line start to go down as the capacitor discharges. So what we've done, we've created a time delay before the bulb comes on, and we can create any time delay we wish based on the value of that resistor and that capacitor. The larger the capacitor, the longer the time delay. The bigger the resistor, the longer the time delay. In activity 6, which is our final activity on transistors, we're going to look at the Darlington pair. In other words, this is a pair of transistors. We're going to be using slightly different transistors, so now we're using a BFY51 as well. You will notice that the output of this emitter follower one that we've used previously now goes to the base of the second one. So whereas previously this went to the gate of the thyristor, now it's going to the base of this transistor, and when it reaches a certain voltage, which we all know to be about 0.7 volts, it will turn on the collector emitter, allowing, in this case, a buzzer to come on. At the moment I've left a bulb in there, but I'll put the buzzer in a moment. So let's have a little look at it work. Now the important thing though, however, is to notice the voltage at this base and the voltage at this base. So I've got 2 voltmeters set up. The voltage at this base and the voltage at the second transistor's base currently are 1.15 and 0.5 of a volt. So quite clearly this voltage at the base of the second one is not yet high enough to turn on my bulb. So I'm going to move my hand over the LDR slowly and watch when the bulb comes on. Watch the second transistor's voltage first of all. 0.67, 0.68, 0.69, 0.7, and the bulb has just started to come on, and at 0.72 of a volt, 0.73, the bulb is pretty much fully on. What do we notice about the voltage at the base of the first transistor? Well, let's just take that bulb back a little bit. You will notice that the base of the first transistor is approximately twice that of the second one. In other words, we're using up 0.7 of a volt to turn on the first transistor, but then we need an extra 0.7 of a volt, if you like, to send to the base of the second transistor. So we need about 1.4 volts on the first one and 0.7 of a volt on the second one. But more importantly with this circuit, I think the Darlington pair is most useful because it has a much sharper switching threshold. In other words, once one comes on and turns the second one on, it is fully on, and therefore whatever's in the circuit switches on almost immediately, as opposed to that slow build-up that we sometimes see, even though I was showing you it very faintly there. So the switching is much quicker. So let's put a buzzer into the circuit. I'm replacing the bulb with a buzzer. And now I'm going to cover up the LDR. And there we go. Now, one important factor, you will notice that there is a diode in parallel with our buzzer. This diode is very important whenever we have any device in the collector circuit of a transistor that has a coil of wire in it, because of what we call back EMF. In other words, large build-ups of voltages when the circuit starts to shut down again, rather than those voltages flow through the transistor down to ground and damage it. What we're doing is, because you'll notice this diode is with the negative to the positive side of the circuit. So in other words, it's in the circuit the wrong way round. It allows large voltages to flow through it in that direction, therefore protecting the transistor. This is sometimes called a flywheel diode or a back EMF diode. So components such as relays, solenoids and buzzers require this diode in the circuit. A bulb, however, did not. This is the end of tutorial 27.